some examples for 6.1. We're going to find out if a probability distribution is legitimate. We will make a histogram of a probability distribution, and I'll show you how to do that with your calculator. And then we'll actually calculate some probabilities that answer C is quite easy. So let me grab a calculator for us so that we can do this.
Yes.
That's where I keep it. All right. Is the probability distribution for X legitimate? Number 1.
Yes.
Each probability and each probability. Number 2. 0.63 plus 0.295 plus 0.065 plus 0.008 plus 0.002. Is it equal to 1? That's what we want to know. Yeah? Oh, fantastic. Hey, let's go ahead and graph this thing.
Yeah.
We could graph this thing just by hand. It wouldn't be that bad, right? We would put 1, 2, 3, 4, 5 on our x-axis, and then the y-axis essentially would be each one of those probabilities, right? Make that you would go between 0 and 1, but it's kind of fun and neat to make our graphing calculator do this. So let's do it. Okay, so I'll get out my graphing calculator. And I'm going to make a new document. In that document, I'm going to add a list and spreadsheet. I'm going to go ahead and call this column X. And I'll call this one PX. It's probability of X or P of X, but your calculator will not like that. If you put P parentheses X, it's going to freak out.
Why?
Because you're making so it does not want you to make a variable reference while you're naming a column. You can make variable references in the field below your title of your column, but not in that one. All right, so what is this? It's a 0, 1, 2, 3, 4. We're going up to 5. We did have 0. Should be there. Ooh, we did not. Sorry. As I said again, just did binomial distributions, so that's throwing me off. Sorry, we need to just start here at 1. So 1, 2, 3, 4, 5. Okay. Over here, we'll have to put each of the probabilities. So let's go ahead and I'll leave that up there. I'll give you guys a moment to put that in. And then over here, I will enter these values, 0.63, 0.29. And did you guys get there? Did I unfreeze it too soon? Oh no, you're good. You can get it from that. All right. Yes. So there it is. We're going to make our graphic calculator calculate and obviously calculate it. Obviously, you can graph this, right? but it's just kind of nice to know how to make the calculator do it. And when we get into binomial distributions and graphing them, we'll really work off of a spreadsheet a lot, so it's going to actually be a lot quicker and more efficient to get your graph off of your spreadsheet. So we're going to hit doc. We're going to insert a data and statistics page. Really all kind of new stuff. We're going to make this variable we're going to make that x. We're going to make our axis x, and then you might be inclined to try to make this px. Don't do it. It's gonna assume that you have some sort of a bivariate relationship, and that's not what this is. So in order to avoid that and tell it and make it say, hey, no, this is not a bivariate relationship, you're gonna hit menu, plot properties, and we're gonna add a y summary list. Okay, add a y summary list. Y. And then we're gonna call that px. And there we go. Undo is Control Z. Oh, hit exit. Yes. Control Z. There you go. Cool. And there we go. We have graphic. So if you needed to, you'd be able to copy that into wherever you needed to. So that's B. We made a histogram. We did it. And so C. What is the probability that a randomly selected student speaks at least 3 languages? So 3 or more, right? Well, we can still use our probability rules to say that, right? So this right here, that's the probability they speak 3 languages. That's the probability they speak 4. Probability they speak 5. So probability 3, we're going to use some notation now. So if I wanted to say probability x is greater than or equal to 3, it's going to be the same thing as the probability that x is equal to 3 plus the probability that x is equal to 4 plus probability x equals 5, which then is going to look like 0.65, 0.065 plus 0.008 plus 0.002, which is we did it. Let's do another one. Yay. We did it. We did it. We did it. Hooray. I know you can do it. Come on, let's up and do it. No? Say it's swipe or no? Here's a way better problem. Has to do with expected values. I don't know why we keep talking about roulette wheels, but we do. It's good for probability, right? I think in previous texts they used the game of craps a lot. I think that they switched to roulette because maybe kids started playing craps. Just because I think it's their 3rd edition of the text. Like they literally teach you how to play craps. Like we went through a whole class and I pretty much taught them how to play craps. And they're like, we're gonna go play, and I was like, I'm not trying to encourage you to. So roulette, I think roulette's a little safer because you don't have access to a roulette. So Anyhow, there's a bet called the corner bet, right? And you're betting on one of four numbers being chosen. Seems like you get some better odds that way, possibly. So if you win, you get $8. If you lose $1, right? So here's our values of x, right? And then our probability that that value occurs. They want to know, in the long run, it turns out that a player loses one out of every 34. $1, 34 out of 38 times, right? And 4 out of 38 times they win. So what we're going to actually do is find, so there are a couple ways to do this. You just kind of find the average. I'm not a big fan of that approach. I would like to use the idea of expected value to do it. And actually the solution that they have for this uses just straight up finding an average. And you can see that the average and the expected value are the same thing. But I really prefer to first approach this as the idea of expected value. So remember, our mean, same thing as our expected value, right? Expected value as it's like E of x. So what is that? That is the sum of all x times probability of x. Right, so in this case, that is just going to be -1, right, because that's our x value, times the probability that you get a -1, which is 34 out of 38, plus, right, because we're going to sum that, so this is our first x times our probability of x. Our second x times probability of x is going to be 8 times 4. So this is our mean. When we calculate this, we get -0.0, approximately 0.05. All right, we're talking about money, right? So I would want to round this to the hundredths place because fractions of the cent are only used to steal money from us at the gas pump. So, or to trick us into thinking that we're paying less than we are. So that's it. So how do we interpret this? We're going to interpret this as we would expect that in the long run, right? If we played repeated games of roulette and we made quarter bets, we would expect to, on average, lose about 5 cents, which is not terrible, considering that you can lose a lot more money gambling. Now, interestingly enough, the actual solution to this just finds the average. So just find, like, it actually calculates an average. So their solution, and it's kind of neat because you can see that you get the same value if you calculated it differently. Or kind of see how the two are actually the same. So it turns out that if you lose $1 for every 34 games, then essentially that's -1 plus -1, right? All the way up to there are going to be 34 of those, right? Plus, and then you'll have 8 plus 8 plus 8 plus 8, right? And there are 34 of these. Well, it'll become clear in my next step. Divided by our total, right? You want to find an average, so essentially this becomes -1 times 34 plus 4 times 8 all over 30. And it turns out that if you calculate that, you indeed get negative 0.05. So there's two approaches to the same problem that are actually the same. So it's kind of cool to look at it in both ways to see that, yeah, actually, indeed, when we're calculating this expected value, we are finding a mean, really in the traditional way that we would find mean, but it's just a condensed version. It's kind of nice. Okay. And so now we'll actually compute the mean using our formula for expected value. And also, keeping in mind that we can find this on our formula. And this is right there. So we have the mean and the variance of a random variable here. So that's what these two formulas are for. For a discrete random variable, I should say, more specific. Alright, so let's go ahead and use those formulas in order to calculate the mean and the standard deviation of these. I think you'll find also that you're getting the variance in your formula here. So of course we're going to have to take the square root of that in order to find our standard deviation. Alright. Let's do it. So we're looking for the mean of our random variable x, which is the same thing as the expected value of x, which is going to be the sum. That's an interesting sigma. A graffiti sigma, I think. Something. Okay. We're going to take the sum of all x times the probability of x. So that is going to be 1 times 0.63. Is this the same one? It is. The same one as we used previously, I believe. Yeah. All right. So I'm going to show you how to do that with your calculator as well. Every place where we can learn how to save time is really crucial. But I first want to write out what we're actually doing. All right. So yeah, we actually have this entered in our spreadsheet here. So if I insert a calculator, I can actually get that sum using the sum function. So I'll go ahead and insert a calculator. And in order to access the sum function, you just hit SUM. Okay. And then in my parentheses, I've actually given it a name, right? All these probabilities, I've called it PX. So let's go ahead and put in PX. My bad. Hey, it's a legitimate probability distribution. Sorry, we're going to have to put a different table in there. So we're going to have to I jumped ahead of myself. Let's call this product. So PROD, and we can make that equal to x times px. It's asking, hey, if you go all the way down to the end, right, A, B, C, D, E, F, right, there's an x column. So it's asking, hey, do you mean the x column, or do you mean this x variable that you just defined? And I'm going to tell it, I mean variable. So I'll click that and see. I'm talking about a variable. And now we're good. And so, skip this step. Now we can go to our calculator. Now that we have those, right? So this is every x times probability of x. And then now I can go to my calculator, and instead of putting some px, I'm going to do some of where I named it, which is prod, P-R-O-D, and there's our expected value. So 1.457. What does that mean? So what were we talking about? We're talking about selecting a U.S. high school at random. These are the number of languages spoken by a randomly selected student. So what does that mean? That means that if we were to select a bunch of students at random from different high schools, we would expect them to speak around 1.5 languages. I feel like that's what I speak. Spanish is not good. So, yeah.
Does that mean you would speak one language and understand?
Yeah, either that or. All right, let's check out the standard deviation of this random variable. So the first thing we're going to do is we have a formula for our variance, right? So that is our variance, which is the sum of all x minus the expected value of x squared times the probability of x. Yes. What is what?
All of x.
All of x. What do you mean all of x? The sum of all of them.
Oh.
Sorry, I see it's like olive. Okay, no. Olive juice is what you can mouth to someone if you don't want to say those 3 words. No? Yeah, get it? Sorry. No, it's the sum of all of our x minus our mean time squared times probability of x. Now this could take a long time to calculate, right? Because if we write this thing out, it's going to be 1 minus 1.457 squared times 0.63 plus 2 times 2 minus 1.457 squared plus, and we're going to go some stuff in the middle that you should know about considering our pattern. And then we go all the way up to 5, right? So 5. My bad, I forgot something. Times 0.29 plus. And by the way, doing this is perfectly acceptable on the AP exam. You can skip a few. A little 1, 2, skip a few, and then continue on. So 1.457 7 squared times 0.002. I'm sorry, that got really small. So I'm going to let my calculator do this for me. I actually probably didn't need to put this second one in there, but it's just better to show that that's the pattern that I'm going off of, so I can skip it. Let's get the calculator to find our expected value. So let's go ahead and go to our Inspire. We've already got this thing set up here, right? So now what we'll do, so now we're going to make a fourth column. And I'm just trying to think of what to call it. I'm not very creative at this point. I want to make it meaningful, but I think I'm just going to name it Joe. So Joe is going to be equal to. So this is where we're going to calculate. So in this one, we're actually going to calculate this x minus the mean squared times the probability of x. That's what we're going to calculate here. So I'm going to tell that, I'm going to say that Joe is going to be equal to, and we're going to, in parentheses, we're going to put x, this is the variable you defined in column A, minus our mean, which we determined was 1.47, 1.457. 1.457. We're going to take that quantity and we're going to square it. And we're going to multiply it times px, which was our probability of x. And that is going to spit out all of those x minus mean squared times probability of x. Should fill in the entire column. I just have to tell it, hey, I'm not talking about the column. I'm talking about the variable. And there they are. So now, what do I need? I need the sum of all of those things, right? I need to add them all up. So I will go back to my calculator, and I will hit sum Joe. I will come help you out. And so that is going to be our variance. We are not done yet, right?
It's because you spilled your water. We were just
So this is our variance, right?
Oh.
So we're not done yet, right? We need the square root, right? So our variance, 0.45 approximately. So this is,
Okay, so you never.
but that's our variance, right? Our standard deviation is the square root of our variance, which is the square root of 0.45, which is probably actually going to be not an exact answer. So I'm going to go awesome function. You can hit that, and then you can just go up here. Paste it in. Paste this. Paste it in there. Okay. And that's going to be approximately 0.671. 671. Huh? How did I paste it? I will show you. Approximately 0.671. So it also asks us to interpret this in context. So what does that mean in context? It means that if you were to grab a bunch of students out of high school classrooms, you would expect them to speak between 1 and 2 languages, right? But that number is going to be off on average by about 0.671. Right? So there we go. Complete with our interpretation. I do believe that does not conclude. Like we have one more to do. I thought we only had 3, but it looks like 4. One?
You lie.
One problem on the...
You said 1AltExamples.
Oh yeah, no, sorry.
You lie.
I was just wrong. I didn't really do it on purpose. Okay, being wrong. Being wrong. No, I did that on purpose. Okay, I'm an honest. Okay. Alright, the weights of 3-year-old females will closely follow normal distribution with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Randomly choose one 3-year-old female and call her weight X. Rude.
Yeah, that's
What is the probability that a randomly selected 3-year-old female weighs at least 30 pounds? Okay, hey, it just said normal distribution, mean 30.7, standard deviation 3.6. Remembers this? It's normally distributed, so doesn't that mean that it should look, that the distribution should look, see? Our mean should be right over here. So what are they asking for? A selected 3-year-old female weighs at least 30 pounds. 30 pounds or more, right? So where is that? That's somewhere over here, right? What are we being asked for? In this shaded region. So, remember how to do this? Remember, z is equal to x minus mu divided by sigma, which in this case turns out to be 30 minus 30.7 divided by 3.6, which gives us a z value, a standardized value of negative 0.7 divided by 3.6, which turns out to be negative 1.944. It repeats, it's approximate. All right, so we could go to our z-table, right? And we could find a z-score for this. I have my calculator out. I don't have the z-table out, so I'm going to go ahead and use my calculator. So I'm actually going to use the calculator function. All right, so we're going to go menu. Statistics, just a review of how to do this using your calculator. We use distributions, and we're going to choose normal PDF. Our x value is 30. Our mean was 30.7, and our standard deviation was 3.6.
Yeah.
And there we go. We get an area of 0.109. So the shaded area is 0.109. So now I'm going to introduce, or I'm going to use the same notation that we use. We're going to say the probability that x is greater than 30 is actually the same as 1 minus the probability that x is less than 30, right? Because that's really what we just got. So that's 1 minus, right? Because remember, what our calculator is giving us is the shaded region, the area of the shaded region to the left of our x value, but we're finding to the right. So that's why I'm saying the probability that x is greater than 30 is equal to 1 minus, right? You've got to take that common. So, why thank you, my hair does look nice today. 1.09. Sorry, it was 0.09. 0.109. What? Always. There's a lot of things to think about at once. It's like I always wondered how Bob Ross paints. The way that he paints, but he talks the whole time he's doing it. Like he doesn't even need a comment. Pure talent. But I mean, it's difficult to talk and think about things at the same time. Occasionally, the wires get crossed, or the signals get crossed, I guess you can. All right, so there it is. The probability is 0.891. We did it.